So here's an extra to go with the careful definition of a limit sequence videos. And I want to go back to the first example, or one of the first examples that we did, which was what is the infinite sum, 1/2 plus a fourth plus an eighth plus a 16th, etc. What's the limit of all those partial finite sums? So why would you do that? And I think it's cool to look at a pretty explicit example. And for me, it gets at, again, the idea of what is the meaning of a limit? Why do we do these idealizations involved in limits a lot of the time? So we're going to have a game, a gambling game, basically, about flipping coins. And so you're going to pay X amount of dollars, and we're going to see, eventually we're going to see, like, how much should you actually be willing to pay for this game. So that's, we're going to leave that open for a little bit. And then I hand you, one after another, silver dollars, dollar coins, whatever, silver dollars. So things worth $1. Coins worth $1, and you flip them. So you flip the first one, just leave it down. You flip the second one I give you, until you get tails. So you want heads to keep coming up. And tails is the end of the game, okay? And then you get to keep all the ones that showed heads, okay? And then the question is, how much money do you expect on average? So this is a probability problem. One of the most important things to ask about probability, what's the average expectation, or let's say expected winnings, if you did this over and over again? If we love to play this game and you keep playing this game with me, on average you play 100 times, on average, like, how many times, what's your total net gonna be? So for each time you play the game, on average, how much do you expect? And what that helps us answer is, if you play this repeatedly, gives us an answer for how much should you be willing to pay the game. If, on average, you're going to win $5 and you only have to pay $3 to play, you want to play this game a lot, as much as humanly possible, because you will make a lot of money. If, instead, the expected winnings was $3 and you pay $5, you shouldn't play this very often. Play it once or twice just for fun, sure, but don't make a habit out of it, because you will lose money to me, and I will be happy, not you. Okay, so we want to know, on average, what's the expected winnings? Well, it's not a particularly hard version of expected value, because, let's see, so on average, expected value, that's just going to be the sum over all the possibilities that can happen of the probability of each possible event that could happen times how much I win given that event. Okay, so first of all, there's the probability, I'll just say P of, I guess. The probability of getting ahead on the first one, on the first flip, is 1/2. It's a fair coin. I'm not trying to trick you with unfair coins or anything like that. Okay. So that's 1/2. All right. So if you get ahead on the first flip, you're guaranteed you're going to keep that coin. So I have 1/2, and so our value for that is we're already up to 1/2, because 1/2 times 1. Okay. Now, the probability of getting 2 heads, which is the way to get any more money on the first 2 flips, okay, well, that's going to be 1/4, because, and we're assuming, again, no weirdness with the coins. It's a 1/2 probability for that first one times a 1/2 probability for the second one. We're assuming they're independent events, is the terminology. And so there's a 1/4 probability that you're going to get a head-head. Okay, so if we were analyzing that completely in isolation, you're going to get $2 from that. But the thing is, I know, as soon as I did that first head, I know I'm guaranteed the $1. So really what matters, what I should add, is simply the $1 extra I get from that second head. Oh, okay. So the added value is the 1/4 probability of getting the head-head times the $1 extra that I get from head-head. Okay. Probability of head, head, head on the first 3 is 1 out of 8. Okay, how much more money does that earn me? I've already taken into account that I'm getting the $2 from the head and the head, head. From the head, 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 I add the 1/8 probability times the $1 extra I get out of that. Okay, so you can kind of see where this is going. I got that 1/2 probability of the $1, and that's kind of a baseline, plus a 1/4 probability of $1 extra. Now I'm sitting on 2, plus an 1/8 times the $3 extra, etc. And so the overall expected value of the whole game is going to be 1/2. Can we see that? Yeah. Plus a 4th, plus an 1/8, plus a 16th, plus ... Okay, and we determined in the second video, I guess, that that was equal to 1. That summation is equal to 1. So what does that mean realistically? Okay, because I think this gets at what happens with a lot of times with limits is that the distinction between the limit, the idealization, and a sort of more practical result. These ... should, if you reflect a little bit on what they mean in this situation, where I've said we're actually playing a game, they should make you a little uneasy, because it implies that we can go an arbitrarily long amount of time, and that I'm willing to let you flip and flip and flip and flip, and get the plus 1/16th, plus 1/32nd, and the plus 1 over 2 to the 100th, or the 1 over plus 1 over 2 to the 1,000,000th. We probably aren't going to play the game that long. There's probably going to be some sort of limit on how long we actually play. So in practice, and this is true for a lot of limits, in practice, we're not really going to add up that infinite sum. But let's say that we don't, from the start, put a hard limit on how far we play the game. We're kind of flexible about how long we go. And we just want to get a really good approximation for the expected value of the game. So if we did have a hard limit and we played like 5 times, that was it. I just let you flip 5 coins and you can get as many 5 coins as at most, then it's going to be 1/2 plus a 4th plus an 1/8 plus a 16th plus a 32nd. Okay, that isn't equal to 1, but it's pretty close. Okay. You know what? That's pretty darn close to $1. It's 97 cents, basically. Okay. So already, even if we only play a fairly short amount of time, it does not take a long time to flip 5 coins, we're already pretty close to that idealized expected value of $1. And if we play 20 times, if I say, you know what, I only have 20 of these coins, and I only have so much time to watch you flip coins, then it's going to be 1/2 plus a 4th plus 1 over 2 to the 20th. Turns out 2 to the 20th, you really can't read that, I'm sure. Sorry. 2 to the 20th is right about a million. Okay, so this is around 1 minus 1/1,000,000th. Okay, so that's really close to $1. Okay, so as soon as you play a decent number of times, our idealized, really simple, easy to remember number of this is worth $1 becomes a really good approximation, even though you're really not going to actually realize the expected value of $1, because you can't play an infinite number of times. You can't even play a billion times. This is not going to happen in your lifetime. Okay, but because of the fact that the limit, as n goes to infinity, of the finite sums is equal to 1, remember what that means. The careful definition of a limit says that the actual values you're really gonna find, depending on, oh, today we don't have that much time to play, maybe today we have a little more time, maybe today we play 50 times, that's going to be really, really close to 1 as long as n is large. And if you go back and unpack the details of the proof, you can even say, hey, suppose I want this to give me an expected value of 99.9 cents. How many times do I need to play? We can answer that question. That answer, it's about log base 2 of, 0.01, things like that. Okay. So the point I want to make, the larger point I want to make, is that often, don't want to say always, but often when we have a limit calculation, it's what I said in the first video, which is it's often a simple, idealized number that's easy to remember or manipulate or elegant, But it's really a stand-in for a lot of more grungy explicit statements of 1/2 plus 1/4 is kind of near 1, and then plus 1/8 is nearer, and then 1/16 is nearer, and also if I want to know how near, I can quantify that when asked to do that. Okay, so the simple takeaway, and this is really what you should take away from this example, is you should pay just about anything under $1. And again, this is if you do it habitually. If you do it like a one-off, then it's just random. You can't make these kind of really simplistic statements. But if you do this every day for a year, then if you pay this person, if you pay me, 98 cents, as long as you make sure that I let you play on average, 7 or 8 or 9 times, you will make money slowly, but you will make money on average. It'll be up and down, of course, with randomness, but eventually you'll make money. Now, of course, if you pay $1.01 or $1.10 of a cent for this game, that's stupid, because you're never going to get above 1 expected value. So that $1 is a very simple takeaway that was coming from the limit, even though I'm not claiming you sit down for the rest of an eternally existing universe and you play this game and do nothing else for the rest of your life. Okay.